Hi, my name is Matt Pizzi, and welcome to my presentation about my recent work called SPY, Car Steering Reveals Your Trip Route. Have been getting increasingly connected in recent years. Data connectivity, that means vehicles equipped with some sort of LTE or 5G, were standing at 20% in 2016. 2020, this jumped to 75%, and by next year, it's expected that 98% of all new vehicles sold in North America and Europe are going to be equipped with a data connection. With this increased data connectivity, this will also open the doors for car manufacturers or OEMs to make revenue out of it. This can be done in two ways. They can sell the data to advertisers, or they can implement an app store and share the data with interested third-party apps. In order to understand this work, we need to first start and discuss who collects vehicular data and what vehicular data they collect. So let's start with who collects the data. These can be native platforms, like native OEM platforms like BMW Car Data or from Mercedes. There's other companies like Usage-Based Insurance, Progressive, State Farm, and other companies that collect vehicular data. And new in the game is Android Automotive, which is a native built-in Android operating system inside the vehicle that runs on the infotainment unit. And what data can be collected? There is a myriad of sensor data and other information that can be collected from vehicles. It can range from powertrain-related information such as vehicle speed or torque or steering wheel angle to body-related information like seatbelt status or airbag status and many more. And now we have to ask ourselves the question, how is this data collected? And in order to do that, we are going to look at an example that's been derived from BMW Car Data. So we have our third-party application provider, Mallory, and she offers a third-party app. And Alice is the customer of this OEM, and she wants to install Mallory's third-party app from the OEM's App Store. And just like in mobile operating systems, you will see a pop-up dialog. These are the permissions that this app requires. Are you okay with it or not? Are you going to authorize it? And if Alice decides to authorize the app, the data first will be transferred to the backend of the OEM. And then the OEM will share a copy of this data for further processing to the third-party server over the OEM's business-to-business interface. And we can already see like a huge problem here. The data will be then in the hands of a third party. And if the third party is malicious, they can do whatever they want with the data once they have it. And as we can see, the increased connectivity does come at a price. So it opens doors for data monetization, but it also opens the doors for privacy issues, privacy concerns. And in recent years, these are unfortunately also on the rise, like the Facebook Cambridge Analytica incident and the European Union deciding to implement privacy protection laws called GDPR. And the question now is, of course, we have more regulation and people are more aware of privacy in recent years, but does this also apply to the vehicular context, to the vehicular ecosystem? And start talking about the first part. Do we have more regulation in the vehicular context? GDPR is fairly new, and these novel data collection systems in cars, these telematic platforms, are also very, very new, and they're just about to start getting implemented into cars. So there's not a lot of GDPR research on that, unfortunately. The only existing regulation documents by the time of the writing of this paper were some voluntary guidelines that were written in 2014, so non-binding for OEMs. And besides other things, OEMs, these documents stated that OEMs only have to ask explicit consent for 3 categories of data, which they define as driving behavior. So this is basically information about how a person drives a vehicle. Concrete examples that I stated in this document are vehicle speed, seat belt use, and information about braking habits. Then geolocation, and finally biometrics, which they summarize as covered information. So much to regulation, and how about the awareness? In order to assess the sentiment of potential customers towards how sensitive vehicular data is. We conducted a survey, and we asked them two very similar sounding questions. How much do you agree to share the following data types with an OEM and with a third-party app provider? And we also gave them some examples about what these OEMs and app providers could be. So we used 20 data types, and we introduced a 5-point Likert scale, ranging from strongly disagree to strongly agree. And this is an overview of our setup. So we recruited 100 participants from Amazon Mechanical Turk. You can see some demographic information on the slide. And these are the results. Basically, we can see that these are very sensitive sensors from the vehicle, like location or speed, whereas others like temperature, make, model, year, here are not super sensitive. From these results, this is an average result from both the answers to the OEM and the third party, but we can say from what we've seen that the mean for the OEM is a bit higher than for the third party, which means that customers or participants trust native OEM apps a bit more than third-party apps. One particular sensor is this one that I indicated with a different indicator here. It's a steering wheel angle. And this is what we're going to be looking at during the rest of the presentation. And we can see that the steering wheel angle is pretty much in the middle. So it's got an average response. People are not super sensitive about it, but they're also not reluctant about it. And this is exactly what we're going to exploit in this work. In the problem statement, we can say that we want to infer the driver's location from the steering wheel angle. And this is much more viable, possibly, than using the speed, as you can see, because the speed is much more sensitive. This leads us to why this attack is actually feasible. It's not only the survey that we saw, it's actually 3 reasons that contribute to this. First of all, it's the weak architecture design. As we saw in the threat model, the permission model can be very coarse-grained, like researchers showed in Android Automotive case. And for the OEMs, the review process is not standardized, and it does not have to be very strict, especially with a rising number of third-party apps. Furthermore, lacks privacy regulations. As we saw, there's only some voluntary guidelines with some vague recommendations, and nobody really knows how to apply GDPR yet to this context. And finally, the lacking user awareness. And the survey basically showed very well that the steering wheel angle is not a very sensitive enough sensor. And all these 3 reasons contribute to this privacy attack that we're going to conduct. The location inference or travel route reconstruction through steering wheel angle is extremely tempting. And we're going to do this by introducing a novel technique called ROCUMA, which stands for road curvature matching. And this is pretty much explained in the figure here. The blue trace is a steering wheel angle, while the orange trace is the road curvature. And as you can see, they're highly correlated with each other. In this case, 0.93. An assumption we have to make in order for ROCUMA to work is that we have to know roughly the geographical area we're conducting it. So we need to know where the victim lives, like in what city, for example. And this leads to our system design. So as input, we have the victim's steering wheel angle trace that got collected by these telematics platforms. And we are also going to have a ground truth database of road curvatures that we can derive very easily through publicly available map APIs like Google Maps or OpenStreetMaps, which we're using in the experimental study of this work. So this is one road in Ann Arbor, Michigan, and the red dots indicate intersections, so where the driver can turn right or left. And the road portion between 2 of these red dots, we're going to refer to that as road segment in the following. And the curvatures are calculated for each of these road segments and stored in a database. Then the attacker is going to take the victim's steering wheel angle trace. Since the victim's not only going to go only on one road for their entire trip, but turn at some point, we need to split it into different unique sections and determine where turns are, like left turns, right turns, and U-turns. After we have that, after we split the entire trace into different sections, We're going to for each of these sections, we're going to calculate the road curvature. And we're going to exploit a correlation. We're going to train a linear regression model with some training data that we have. And then we will know how to calculate the road curvature for the attack data. Next, we can start matching the calculated road curvature with the derived road curvature from our ground truth database. And we got to start with one section. We define the salient section, which is the initial section, as the one with the highest average curvature in that area, which is basically depicted here with a red circle. So we're going to start matching this, and a section is basically just nothing else than one road without any turnings. And we're going to calculate the dynamic time warping score, the DTW score, for each road segment individually and for combinations of it. So in order to depict this, we have a very easy example here with only 5 road segments. And we will go through the entire search space of all road segments possible, and then start matching the calculated road curvature for that section with the first road segment. So this would be, in our case, be this area, and then we're going to do it with the second, the third segment, the fourth segment, and the fifth segment. Of course, the driver is not going to turn at every intersection, so we also have to consider, as I've said, combinations of road segments, so combinations of 2, and then we will look at 3, and so on. You get the gist. And then we will match the remaining sections, which is much easier since we already know where the salient section starts and ends. So we only have like a limited amount of possibilities to go through. So this is the salient section, and what we're going to do is we're going to match the preceding and succeeding section, so these two. And this goes on recursively until the entire trace is processed, and then this ends, and we will have the matched route. One thing that I want to mention is that we have to manually pre-process the steering wheel angle trace from the victim first by cutting the first couple seconds and the last couple seconds. And this was because usually when the victim starts a trip, they back out of their driveway, or they drive into a parking lot when they end their trip, and this messes up with Rocuma, and that's the reason we had to manually pre-process it and cut it out. So for our experimental setup, we used 5 different vehicles from the same OEM, Ford. We collected 58 traces in total by using the OpenXC platform, which gave us access to the steering wheel angle parameter in these Ford vehicles. And for the road curvature, we used OpenStreetMap API to derive them. Here in the data set, you can see some statistics about the 58 traces. So we conducted all our experiments in the city of Ann Arbor, Michigan, which consists of 236 roads and a little bit more, about 2,700 road segments. The maximum trip length was 20 miles, and the average was around 4 miles. The most important thing is accuracy. How did Rocuma do? And in 41 out of 58 cases, we could match the entire route from start to end, which accounts for 71% accuracy. And we also wanted to see if it really depends on if it's a short trip or a long trip, and we saw pretty much that it's independent of the attack trace line, which is very good. We also wanted to look at how it behaves just matching the initial section, because we're doing this on the entire search space. And in 44 cases, we could match it. So this means that in only 3 cases after matching the initial section, Rocuma could not match the remaining sections with a smaller search space. And we wanted to explore and explain why this happened. And this is basically the reason for all of these cases. So it had to find this correct intersection, but it found the preceding intersection. And the reason is this last final road segment is relatively straight and not curvy. And this is where Rocuma runs into troubles. So what we can see here, the lessons learned are that the success heavily depends on the initial section, and the straight final segments can cause issues with Rocuma. Other metrics that we benchmarked are the memory footprint. So how big is it to store the entire ground truth road curvature database? For Ann Arbor, it was around 30 megabytes, which was 55 kilobytes per mile. And if you extrapolate it for the Detroit metro area, which has more than 5 million inhabitants, it's around 26 gigabytes, which is not a lot for an attacker. And in terms of computation time, we conducted our experiments on a fairly low-end setup. And we found out that the maximum time to process Rockuma took less than 19 minutes. And so most of it was for running DTW, and initial section matching took more than 99% of the entire time. So the big question is, are these experiments really applicable to other cities? We only used one city to conduct our experiments in. And we wanted to at first start with a theoretical analysis, and we looked at other cities from North America and Europe of varying size, which you can see in the number of road segments it has. And we calculated the average curvature index, which is basically, the equation is here below, and it's basically saying how curvy is a road on average in the given city. And some cities are lower, these are depicted in red, and some cities have a higher average curvature index, which is in green, which basically would theoretically mean that higher curvature index, that it's more likely to work, and the ones in red, not as likely. But a second factor is the similarity of the road, of the curviest roads in a city. Because again, the bottleneck is matching the initial section, and we're going over the entire search space here. And the less similar the curviest segments are, the better is our chances to actually get the right segments. And similarity can be expressed by the standard deviation sigma of curvature values. A larger sigma results from more distinct and less similar road segments, whereas a smaller sigma represents more similar road segments. So we can see that although for San Francisco we have a lower average curvature index, here we have less similar curviest segments, which might actually imply that Rockuma could work in San Francisco. We also wanted to quantify this and see, given on the data we had, if we could run some experiments and get some conclusions out of it. And so what we did is we defined a new area with a higher curvature, average curvature index in Ann Arbor, which you can see in the rectangular red box. And we ran 15 traces out of these 58 traces in there, because simply these 15 traces started and ended in this area. And the accuracy was surprisingly relatively high. It was in 13 out of 15 cases we could match the route completely from start to end, which is 87%. And although this is a very limited evaluation, we can say that an area with a higher average curvature can yield higher accuracy. We want to compare our work with related work. There is some work on phone sensors that are being used to derive the location of a car. Phone IMU sensors or even the power consumption are leveraged. And then there's other works that actually use the vehicle speed from inside the car. And one big difference of these works are that most of them assume a starting point, which basically means they need to know the initial point where the car started driving, and then they can reconstruct the rest, which is a very, very big assumption to make. And SPI doesn't do that. Furthermore, our accuracy, if you look at the last row, is much higher than all these related. Of course, we have limitations. We saw that, or we think that for most European cities, it will work because they're usually curvier than American cities that are usually on the grid. Just look at Manhattan. It's impossible to distinguish the roads from each other because they have no curvature whatsoever. We need a rough knowledge of the city and the area, but no starting point assumption. And what we also did not consider are lane changes, U-turns, or roundabouts, whereas the former lane changes are, as you can read in the paper, should not be a big problem for Rockuma. And now let's finally conclude this work. So in this work, we showed that driver location can be viably inferred by steering wheel angle data, and we introduced a new threat model. Since vehicular telematics systems are on the rise and They allow third-party apps to access sensitive vehicular data. So the threat is real. We conducted an awareness survey where we showed that drivers are not really aware of the sensitivity and privacy consequences of most automotive sensors. And finally, we showed that Rakuma offers better performance than all service-related work. Yeah, I want to thank you. This is the end of my talk. I'm Matt Pizé, and I want to thank you. I want to thank Xiaoying and my advisor, Professor Shen.